Hello, have a good day. I'm going to publish fourth lecture in the lecture series. This lecture series is going to be published in part by part so that you can easily understand the content in the lecture series. If we go more, so then you will feel bored. So therefore, I'm going to publish short ones, short videos, so that you can easily identify the lecture. So today I'm going to teach give you design lecture number 4. It is part 1. Actually it is part 1, basics in singly reinforced rectangular beam design for flexure. Which is in accordance with BS 8110 part 1 1985. In this lecture series I'm not going to teach you how to design deep beams, that is the beams of which clear span is less than twice the effective depth. These effective depths and those epsilon s here, h, d, x, b, will you can learn all these things by following this lecture and another other lectures. So in this lesson 4 there will be 4 parts. I will publish one by one those 4 parts. So actually in this case it will be advisable to have the code. You can easily download this BS 8110 part 1 1985 code from Google, and you read it. The relevant section I have indicated the clause and the section related to the lecture in this presentation. So easily you can follow that code according to the indication in the lecture. So if you are using the BS code in line with this lecture series, so you will be able to easily identify what they say, because this lecture series is mainly based on BS 8110 part 1 1985 code. And also I will teach, and also in this case I am going to teach you only the basics, and after that I will teach you how to calculate beam design in one by one. So and also we will teach you how to draw shear force and bending moment diagrams. So let's move to the content of full lecture regarding the beam design. Introduction, design beam for flexure, design resistance of moment of beams under and over reinforced beams, design formula, design procedure in the code. That means in this lecture there will be 6 parts, and today I am going to teach you only the introduction. So let's move to the introduction. So you can read. I earlier told you that it would be better that you have a BS code with this lecture. So you can read clause 3.4 in BS 8110 while you referring to this video. So then you know that there are in this lecture I am going to teach only designing of singly reinforced beams, but you know actually in another lecture I will give you all the details of other reinforced beams, that means doubly reinforced beams. There are 2 types of reinforced beams. First one is singly reinforced beams, and second one is doubly reinforced beams. You know that in singly reinforced beams you can see this figure easily. You can see this figure in this video. So let's think that this is a beam. If you are loading here at the top of the beam, this beam tend to bend. So this beam will bend like this. Then that in this case you can see this picture, and this is the beam before loading, and after loading this beam will bend like this. due to loads. So this is, you think that this is the cross section of that beam. So when we load this beam on top, in top fibers, that means top section will get compressed, and the second section will be in tension. That means it is subjected to pulling part. You know that actually the concrete is weak in tension, but very strong in compression. So therefore we have to take care tension loads in the concrete section, because concrete is not provided to resist against tension. Therefore we introduce reinforced steel bars at the tension section like this, tension area like this. So if you are providing steels only for tension in a beam like this, we call it is a singly reinforced beams. But in sometimes the beam section will not be adequate, that means to resist compression force as well. You know that if the beam section is very small, the concrete part above at the compression side will not be adequate to resist the compression force. In that case you have to provide additional reinforcement to additional steel bars to take that compression force. In such beams, that means beams in which there are both compression and tension reinforced force, both tension and compression bars are called doubly reinforced beams. We are not going to teach you on the doubly reinforced beams. We are learning on singly reinforced beams. Actually we in the site we identify more doubly reinforced beams than singly reinforced beams. But actually in both type of beams there are in bottom part steels and top part beams. In singly reinforced beams actually there are sometimes two bars in top in compression side. That is not due to take compression forces, but that is to have a firm shape of the that beam that means to maintain the figure of the beam. And you have to put shear links. I will teach you how to provide shear links, and those things are tied on that beams, that bars. So you remember those top bars are not provided for compression forces, but in singly reinforced beams that is only to have a firm shape of the beam, so that we can easily cast in the site. So that is the main thing of singly reinforced beams. And also you should know on the effective depth. What is called effective depth? Actually effective depth is extreme compression fiber distance between the extreme compression fiber to the centroid of the top tension reinforcement. That means from top of this compression fiber to centroid of this steel area. You can easily see in this figure, this is called D. It is effective depth. And after that there are another categorization of beams. That means in accordance with the supporting, we divided to beams in some parts. So first one is simply supported beam. And also you know that you can see in this figure in here A, this is a roller support. That means this support can move and take no moment here. And also this kind of support at B, this is called pin beams. There is no movement here, and he take no movements. And also here you can see when you are drawing bending moment diagrams, here bending moments is 0 at the end of these supports. And such beams are called simply supported beams. Actually in simply supported beams there are in one side there is a pin support, and other side there is a roller support like this. It is called simply supported beam. So when you are dealing with those beams, you have to know what the clear span is and what the effective span is. So actually you know that in actual situation here in this figure in these two are beams, not beams, this is the beam and this is called columns. Then here clear span is LC from face of this column to face of this column. Other support, these two are supports. Let's think that columns, or sometimes maybe these are walls. So clear distance means from here to here, face to face distance of the supports. And when we are calculating effective length, effective span of a beam, we should consider two lengths. First one is center to center distance of supports. In here, from here to here, it's called Ln. And also the other one is LC plus effective depth. That means clear span plus effective depth, this D. Effective span may be taken as small of distance of those. That means in Ln we consider Ln and LC plus D, effective depth. In those two, after considering those two, we take the smaller one as the effective span. So you can easily learn than this when you are doing some calculations. Let's move to another type of the beam. And also you can know that in this regard it has been clearly stated in clause 3.412 in the BS code. And then the other one is continuous beam. Before we move to continuous beam, we have to know about what the statically indeterminate beam is. So then let's think that in this, let's consider this simply supported beam. Then in this beam you can calculate this reaction, RA reaction and RB reaction easily by resolving the forces into horizontal direction and taking moment with respect to point A. In easily you can calculate those two reactions RA and RB by solving quadratical equations, because there are two equations and two unknowns. So therefore easily calculate those reaction. In such structures are called static, are called determinate structures. But indeterminate structures means then let's see that there are two in here we have to calculate 4 reactions, but you can only derive 2 equations by this from horizontal direction forces, equilibrium, considering the horizontal direction equilibrium, and taking moment at any of supports. There are 2 equations but 4 unknowns. So in that case you can calculate these 4 reactions. That means this support reactions. You can't calculate. In such case, you have to take you have to consider another method. So I will teach you that method, deflection method. So whatever it is, I will teach you in another in an another lecture series. So this is just to remember, just to have some idea. So in that case, this is called that means there are lesser number of equation to calculate support reactions. In such kind of structures are called statically indeterminate structure. In continuous beam, actually it is a statically indeterminate structure with multiple spans. Here means in simply supported beams you can see only one span. So you can see only one span in here from A to B, one span. But in continuous beam there are in here in this example there are 3 spans, but it may be 2, 3 or 4. And sometimes in here these are roller support and there it is pin supports. There may be some fixed supports, and also sometimes there may be free here, that means free end here. So whatever it is type of a continuous beam. In this case we calculate normally effective span as a distance between supports from this center of support to this center of support is taken as distance between this support centers is taken as effective span. It is you can clearly read and understand clause number 3, clause 3.4.1.3. and also let's move to cantilever beam, another type of beam. That means you can clearly identify in this figure. In this case, in here it is fixed, that means no movement, no rotation, and in other end is free end. In this kind of beam is called cantilever beams. Cantilever beam, when we are calculating effective length of the beam, we take the distance from that free end to fixed end plus half of effective depth. It is clearly indicated in clause 3.4.1.4 in the code. And also you can easily there are in practically you meet lots of beams. Those mainly those are flange beams. Then you know when you are designing a building, the beams have been connected to slabs. That means continuous flow slabs. That means beams and slabs are casted together. So therefore there is an action in here with the beam. So that action have to be considered when we are designing. Otherwise it will be a over design if we do not consider that flange action. It is called flange action. That means in here let's think that this is the slab. In figure you can easily identify this is the slab and these are beams. When we are loading here, when taking this the load load from slabs transferred to beams, then at the top of the beam the beam action is connected with the slab. That means beam action is connected with the slab. It is called flange action. You can read clause 3.1.5 to take improve your knowledge. So when beams are casted with a flow continuous slab and support the continuous flow slab, in this kind of beam is called flange beams. There are two types: L type flange beam, T beam, L beam and T beam. In here in corner beams are called L beams because there are no beams slab section there. So therefore not combine action here with the beam. So therefore this is only L shape. You can see this in this corner shape is shape beams, and the shape of the corner beams are L shape. But in the middle beams there are two parts of the slabs which contribute to the combine with the beam. Therefore this shape is called T shape. Therefore it is T beam. You have to know about this BF. BF means effective breadth. That means the breadth which act together with the breadth of the beam which act together with the slab. That means effective breadth. And also this in top that slab section, thickness of slab section is called HF, thickness of the flange. It is called flange, and it is called thickness of flange. And also the below section of the flange is called web. The section below the flange is called web, and it is denoted by BW. So you know that HF, BW you know, and also you have to calculate this BF. So you will learn how to calculate BF when you are doing some calculations. I will not teach you here on the flange beams, but this is to know about the beams. And also in here this effective width, that means you know that this BF you can calculate like this: effective width of the flange beam. For T beams, web width, that means BW plus LZ over 5. For L beams, web width plus LZ over 10. You can learn what LZ is later. So in L beams you know that actually this BF is lesser than T beam, because there are two either side actions of middle beams. But in the corner beams the BF is lesser than BF of that of T beam. In here the BF is equal to that this BW plus LZ over 10 for L beams, and for T beams this BF is equal to this BW plus LZ over 5. You can learn later what's called the actual flange width if less. What's the meaning of that? You don't worry about this, worry on this now. So in this case we take LZ as distance between point of zero moments. You can calculate the distance between zero moments from bending moment diagrams. In continuous beams we normally take it as 0.7 into effective span. You should remember this one. In continuous beams this LZ, that means effective span, is 0.7 into not in continuous beams LZ is equal to 0.7 into effective span. Design of flange beam will be discussed later in future lectures. So thank you for watching IETV. I will publish next lecture, that means part 2 of this, as soon as possible. Thank you very much.